Welcome to the Deep Dive. So today we're jumping right into the future of materials engineering, really looking at how engineers are building those, next-gen supermetals.
Yeah, the components that make our planes lighter, cars more efficient, machinery just lasts longer.
Exactly. And we're diving deep into metal matrix composites, or MMCs, and the focus really is on one crucial challenge. How do you make them stronger, but without driving up the costs like crazy or, impacting sustainability?
Exactly. I mean, engineers are always chasing performance, right? But there's always this pressure to find a sustainable, low-cost approach. And the foundation here is the AA7076 aluminum alloy. It's kind of the backbone for a lot of modern aerospace structures, prized for that strength-to-weight ratio. But the question is always, okay, how do you supercharge something that's already pretty good?
And the answer, according to this really interesting research, involves something that sounds like it came straight out of a volcano, perlite nanoclay. This is the secret ingredient, apparently. It's naturally occurring, easy to get hold of, a volcanic aluminosilicate, basically volcanic dust that happens to be chemically just right.
It really seems like the ultimate low-cost solution. And what's truly remarkable here, I think, is the reinforcing efficiency they got. This study didn't just, nudge the performance up a bit. It achieved a shocking 38% improvement in tensile strength. And get this, using only 1.5 weight percent of this nanoclay.
Only 1.5%.
Yeah. I mean, when you compare that tiny amount to traditional reinforcements, you often need 5%, maybe 10% ceramic content for similar gains. So this looks like a massive leap forward for manufacturing costs and sustainability.
Okay, that sets the stage perfectly. So cheap volcanic material, turning it into aerospace-grade components. Fascinating. Let's lay down the foundation then. What exactly is AA7076? Why this alloy? Why spend resources trying to make it even better?
Right. So AA7076, it's part of the 7000 series aluminum alloys. These are basically the toughest ones out there. It's an aluminum base, but it's heavily alloyed. Got about 7.0% zinc, 1.2% magnesium, other bits too. Think of it like this. 6000 series aluminum, that might be in your bike frame. Strong, yeah, but workable. 7000 series, that's the heavy-duty stuff. Critical load-bearing parts in jets, high-performance forged bits in cars, places where stiffness and safety are just non-negotiable.
Okay, so that's the high-tech, robust matrix. And then contracting that, we have the star of the show, perlite nanoclay. And you mentioned, we need to be clear, this is not perlite, the steel thing.
Absolutely not. Completely different.
So what is this stuff, chemically speaking?
It's essentially amorphous volcanic glass, or rock. The main components are silicon dioxide, SiO2, and aluminum oxide, Al2O3. We don't need to get bogged down in the exact percentages, but the really key thing is its size. The average particle size is tiny, like 80 to 100 nanometers.
Nanometers.
Yeah. Plus, it has a really low density, so a little bit weight-wise goes a very long way in terms of volume and surface area. It's basically the definition of a cost-effective nanofiller.
All right, so we've got our light, strong metal matrix. We've got our incredibly tiny, cheap reinforcement. Now, the big question in composites always comes down to mixing, right?
Yeah.
Dispersion. How do you actually combine these things without the tiny particles just, clumping up?
Good question. They used a technique called motorized stir casting. It's a liquid state process, so you melt the metal, generally favored because it's relatively inexpensive and, importantly, scalable for industry. The process was pretty specific, though. They melted the AA7076 at 650 degrees Celsius. And crucially, both the molten aluminum and the nanoclay powder were preheated to 400 degrees C. That helps with wetting, getting the liquid metal to properly coat the particles.
Well, it's stir casting. Isn't that sometimes seen as a bit, basic, like maybe prone to defects or not getting that perfect dispersion, especially with tricky nanoscale stuff?
That's often a concern, yeah. But it seems like their execution here was spot on. They used a constant, pretty high stirring speed of 400 RPM. That fast stirring creates these deep vortices in the melt.
Ah, like a whirlpool.
Exactly. And that forces the nanofillers to spread out evenly before the whole thing solidifies. They tested just two concentrations, both very low, 1.0 weight percent and 1.5 weight percent.
Okay, let's check the tape then. Section 2, microscopic validation. Did this relatively simple stirring method actually work? Did they get that even mix?
Well, according to the results, yes. A resounding success, actually. They used scanning electron microscopy, SEM, and also energy dispersive X-ray EDS analysis. The SEM pictures, the micrographs, they confirmed the nanoparticles were almost entirely uniformly distributed, mostly along the grain boundaries of the aluminum matrix.
And the big worries, clumping agglomeration or trapped air bubbles porosity. Those can kill the properties.
Minimal. That was the key finding. Minimal agglomeration, minimal porosity, which really confirms that this specific customized stir casting setup was highly effective for this particular combination of materials.
Okay.
And the EDS analysis, that just backed it all up. It mapped out where the elements were, showing uniform aluminum and zinc from the alloy, and confirming the bits from the nanoclay were integrated right in there. The structure looks sound.
Excellent. So the mix was good, foundation laid, structure looks perfect. Now for the payoff. Section 3, the mechanical boost. Let's start with hardness. For you listening, hardness isn't just about dents. It's about resisting scratches, wear, localized deformation. Means parts last longer under friction.
And the hardness results were, well, pretty impressive. The base AA7076 alloy measured about 82 on the Vickers hardness scale, HV. Adding the nanoclay just jumped those numbers right up. At 1 weight percent, they saw a 17% increase. But the best one, the 1.5 weight percent composite, that hit a 32% enhancement in Vickers hardness.
32% harder. From just 1.5% of volcanic dust.
Exactly. That's a massive improvement in surface protection from a tiny addition.
Wow. Okay, surface is tougher. But the real test, especially for structural parts like, say, a wings bar, is tensile strength. How much stronger is it before it actually breaks under tension?
Right, and this was really the headline finding. The base AA7076, its tensile strength was about 106 megapascals MPa. The 1.5 weight percent composite achieved over 146 MPa.
Okay, do the math. That's a 38% improvement.
38%. And the core strength of the material, I mean, just to give you some perspective, that jump of around 40 MPa, that's kind of like the difference between, say, basic mild steel and a decent medium-grade structural steel. It's a significant leap.
So we're not just tweaking it slightly. We're fundamentally changing its load-bearing capability with volcanic dust.
Seems like it. And the stiffness, too, measured by the tensile modulus, that also jumps significantly. From about 1.33 gigapascals GPa up to 2.21 GPa.
Okay, but there's always a catch, isn't there?
Right.
We often talk about the strength-ductility trade-off. You make metal stronger, harder, usually gets more brittle. Did they lose ductility here?
They did, yes. That's the typical trade-off. The maximum strain, basically how much it can stretch before snapping, decreased. It went from 12.2% in the base alloy down to 8.9% in that optimized 1.5% composite.
So less stretchy.
Less stretchy. But, you know, for many structural applications where ultimate strength is the absolute priority, think fixed engine mounts or something, that huge 38% strength gain is probably well worth giving up a bit of that elasticity.
Fair enough. So why? Why is it suddenly so much stronger? What's happening down at the nanoscale with these perlite particles?
Well, the researchers point to three main mechanisms, all thanks to that really good dispersion they achieved. First, the nanoscale perlite particles act like tiny roadblocks. They physically block the movement of dislocations in the metal's crystal structure.
Dislocations are like imperfections, right? The things that let metal deform and eventually break.
Exactly. Blocking them makes it harder for the material to deform. That mechanism has a name: Orowin strengthening. Think of them as nanoscale speed bumps for those defects.
Okay, speed bumps. I like that. What else?
Second, they observed strong interfacial bonding. The connection between the nanoclay particles and the aluminum matrix is really good. That strong bond means when you pull on the material, the load gets transferred efficiently from the softer aluminum to the hard nanoclay particles. Stress gets spread out better, not concentrated in weak spots.
Makes sense. And third?
Third, it's about the grains. That fine distribution of particles leads to something called grain boundary pinning.
Grain boundary pinning. Okay,
Yeah.
break that down. What does that mean for the material?
Basically, the tiny perlite particles sit at the boundaries between the individual crystal grains of the aluminum as it solidifies. They get in the way and stop those grains from growing too large. The result is a much finer internal grain structure overall.
And finer grains generally mean stronger metal.
Yep. Finer grain structure equals a stronger material. It's a well-known strengthening mechanism.
Did they look at how the samples actually broke? Did the fracture surfaces confirm that better bonding in the 1.5% sample?
They did, and it lined up. The weaker composite, the 1% one, failed with a relatively flat, kind of smooth fracture surface. But the optimal 1.5% composite, its fracture surface was much rougher, more complex. You could see features like dimples, river lines, signs of particles being pulled out.
Which means the crack had a tougher time getting through.
Exactly. It shows the crack had to work harder, navigate around those strongly bonded perlite particles. Indicates higher resistance to crack propagation, bitter toughness, essentially, despite the slightly lower ductility.
Okay, so it's stronger, tougher surface. Let's move beyond just pulling it apart. How does it hold up to wear and tear? Endurance. If you're building, say, a lightweight brake caliper or maybe a moving part in a suspension system, it needs to resist grinding away. What did the wear tests show?
They did dry sliding wear tests using a standard pin-on-disc machine under different loads 10, 20, and 30 newtons. And that strength improvement translated directly into better endurance. The 1.5 weight% composite consistently showed the best wear resistance. They measured up to a 39% reduction in the wear rate compared to the plain AA7076 alloy.
39% less wear. That's huge for component lifetime. Means parts could last almost 40% longer before needing replacement. Big cost saving.
Absolutely. Commercial impact right there.
So how does that tiny bit of nanoclay physically stop it from wearing down? What's the mechanism there?
Well, it's partly that increased bulk hardness we already talked about. Harder surface resists abrasion better, plus the improved load distribution helps. But when they looked closely at the worn surfaces with the SEM, the 1.5% sample showed much narrower wear grooves, a smoother surface overall compared to the deeper gouges on the base alloy or the 1% sample. The analysis suggested it's mainly resisting what's called two-body abrasive wear, basically. Hard particles or asperities plowing through the surface. The high hardness fights that off. They also noted the wear debris, the little bits that came off. For the 1.5% sample, the debris was smaller, flatter, more like fragmented plates. That's often indicative of a more effective wear resistance mechanism kicking in.
Okay, this brings us to section 5, kind of synthesizing all these findings. And the core message here seems to be efficiency, right? This is the real takeaway for anyone listening, especially engineers. Just how revolutionary is getting these results with only 1.5 weight% loading? How does it stack up?
It really could change the game for making cost-effective MMCs. Like we said, a 38% boost in tensile strength using just 1.5 WT% of this, well, relatively cheap volcanic material. Now, compare that. You look at the literature, other studies, to get a similar 38% strength increase in a comparable aluminum alloy using, say, silicon carbide, thick particles, a common reinforcement, you often need way more. One study reported needing a massive 10 weight% of SICKNACs.
Wow. Okay, so let me get this straight. We're talking about potentially replacing 10 pounds of relatively expensive, energy-intensive SICK with just over 1 pound of cheap, naturally occurring perlite nanoclay and getting basically the same strength boost.
That's the implication, yes. It's not just a small improvement. It's an order of magnitude difference in the amount of reinforcement needed.
That's not just a tech win. That's an economic earthquake for manufacturers.
It points towards extraordinary efficiency, the ability to potentially match the performance of composites packed with expensive ceramics, but using just a tiny fraction of a low-cost natural filler. That's probably the most significant finding here.
And they didn't just rely on physical tests, right? They used computer models, too, to validate this.
Right. Crucial for reliability and, convincing people. They used Finite element, or FE, simulations ANSYS Workbench, specifically to predict the mechanical properties. And the results lined up really well. The predicted tensile strengths were within a pretty tight margin, like 5% to 8% of what they actually measured in the lab.
It's good agreement.
Yeah, it confirms their computational model is reliable. Means it could potentially be used for future design work with some confidence.
Okay, but every study has limitations. What were the caveats here? What do engineers listening need to keep in mind before getting too excited?
Absolutely. And the limitations really point towards the next steps for research. First, they only tested 2 very low concentrations, 1.0 and 1.5%. We don't actually know where the limit is. Add too much, and eventually those particles will start clumping, hurting the properties. They didn't find that upper limit.
Okay, so maybe 2% works even better, or maybe it falls apart. We don't know yet.
Exactly. And second, a big one. All the testing was done at room temperature. For real-world aerospace or automotive parts, things get hot. You need high-temperature stability. You need to know how it holds up under repeated stress cycles, fatigue endurance, and how it resists corrosion.
Right, the real-world torture tests.
Mm-hmm. Those crucial factors still need comprehensive evaluation. This study is a fantastic starting point, but it's not the final word for applications yet.
Makes perfect sense. Those are the next hurdles. So wrapping this up, what's the ultimate conclusion you draw from this deep dive?
I think the conclusion is pretty clear. This research has strongly validated perlite nanoclay as a seriously efficient, potentially very cost-effective, and sustainable high-performance reinforcement for aluminum alloys. Specifically, the AA7076 composite with just 1.5 W2% of this stuff offers genuinely superior mechanical properties at 32% higher hardness, 38% higher strength, plus excellent wear resistance. It makes it look immediately viable, or at least highly promising, for lightweight structural uses across automotive, aerospace, maybe even marine industries.
A genuine supercharger for alloys, sourced from something natural and cheap. It really is a great, low-cost, high-performance story.
It is. And maybe here's a final sort of provocative thought for you, for the listener, to mull over. Given this incredible efficiency we're seeing at such tiny concentrations, what happens if you start combining things? Imagine the potential synergistic effects. If future research looks into hybrid composites, say, using this 1.5% nanoclay, plus maybe just a tiny trace of something like silicon carbide, or even carbon nanotubes.
Mixing the cheap bulk reinforcer with a tiny amount of a super performer.
Exactly. Could we unlock even greater performance? Could we push these already high-performing, low-cost materials into territories we thought were only reachable with really exotic, expensive lab-made stuff? That synergy is where things could get really exciting.
That potential for a low-cost super material blend. That's a fantastic note to end on. Really appreciate you walking us through this research.
My pleasure. Always fascinating to see these kinds of innovations.